Okay, this last topic is solution stoichiometry, and it is not really a new topic because individually, all the steps that we're going to show you, you already know how to do. It's just a matter of combining them in context and being able to carry out a problem with many things involved. So, let's say we have a test tube, and in test tube we have copper sulfate solution, right? And let's say to that we are going to mix in sodium hydroxide solution. Now, based on your understanding of solubility rules, you should be able to figure out that there's going to be a precipitate, right? Sodium hydroxide, copper sulfate. If you run through your solubility rules, you should be able to see that copper 2 hydroxide is going to be a solid. Okay? So it's going to form precipitate. And so if we have concentrations and volumes at the start of the problem, which you pretty much always will, you will be able to figure out how much of the product, i.e. the solid, will form. Right? That's kind of the primary goal. And because there's two reactants, because there's two solutions, you need to approach this just like you would a limiting reactant problem. Okay? So let's start off with a balanced equation first. So CuSO4 plus NaOH, right? Of course, they are solutions first, so both of these are aqueous. We get our copper hydroxide, which we assess that to be the solid. And we also have sodium sulfate, which is aqueous. And we'll do some balancing here. It's going to be a 2 there. And that's it. Okay. When reactions result in a solid, we often need to figure out how much there is. So, you are given the molarity and volume of both of these. No, just kidding. You're given the volume and molarity of sodium hydroxide, and they're asking what volume of copper sulfate is needed. Okay, so this one is not necessarily a limiting reactant problem, but it takes you through the same skills as a limiting reactant problem would. The first thing we need to do is use our volume, use our molarity, and find moles. Okay. We have our molarity, we have our volume. We find that there's 0.005 moles of sodium hydroxide. Now, that is your given. What they're asking for is this. What volume of the copper 2 sulfate? Bless you. But we don't know, we can't answer that because we don't know the moles of copper sulfate yet. So the next step involves transitioning from sodium hydroxide moles to copper sulfate moles. So how do I do that? What goes where in my multiplication bracket? Elgin. Okay. Yep. And they're asking us about the copper sulfate. So the copper sulfate should go in the numerator. Okay. So now we know how many moles of copper sulfate are involved. The question, though, is asking the volume. Because, see, we already know the molarity of the copper sulfate, so now we know the molarity, now we know the moles. And they're asking for the volume. So your molarity, you can do this, you can go one of two ways here for your work, right? If you know molarity is moles over liter, then you can go ahead and solve for liters by taking the moles and dividing by the molarity, right? Or you can just use dimensional analysis. And that's actually what I'm going to prefer to use here because unit-wise, everything cancels the way it should. It's really doing the same thing mathematically. Our molarity was 0.2 moles per, right here, 0.2 molar. Everyone see it? 0.2 molar. Well, 0.2 molar means 0.2 moles per liter. 0.2 moles per liter, or 1 liter for every 0.2 moles. We did this a bunch with density back in Unit 1, where sometimes when you have to divide by density, the way you show that your units cancel is to flip it over, so our moles cancel, and so 0.0025 divided by 0.2 is 0.0125 liters of CuSO4 solution. Now, if you don't like that, no problem. Just go back and use the equation over here, right? So you take your moles, 0.0025 divided by the molarity, 0.2, and you will get the same answer because mathematically you're doing the same thing. It just looks different. Okay, what did we have here? We had a reaction taking place that produced a solid. They didn't ask about the solid in this one. They asked how much of the other reactant was needed, specifically the volume. So our first step was to take the givens and find the moles. Our second step was use the mole ratio to convert from the moles of the given to the moles of the unknown. Our third step was to take the moles of the unknown and use the molarity to figure out the volume. This was a 3-step problem. 4 if you count balancing the equation. All right. The crux of these problems is always going to involve the mole ratio. You definitely need a balanced equation. That should go without saying. You write yourself a balanced equation. You should be able to move in and out of moles using the molarity equation, right? Like right away, right off the bat, we said multiply molarity by volume. Well, where did that come from? That came from the fact that if I rearrange this equation, molarity times liters is how we got moles. Right? So these pieces are going to be used over and over again, right? A lot of times in the same order, but maybe not so at the end. Let's try another example. 20 milliliters of 0.2 molar calcium bromide solution and 30 milliliters of 0.1 molar sodium sulfate solution are mixed, right? A balanced equation. Okay. So calcium bromide. Did I mention before that knowing charges and knowing how to write neutral formulas is important? Your balancing will be all wacky if you don't get the formula written down correctly. So calcium bromide, sodium sulfate, okay. So we should be able to predict our product. You know by now this is double replacement. You can check your solubility rules. Calcium sulfate ends up being the insoluble one, so that is our solid precipitate. Sodium bromide is aqueous. And we just balance this, put a coefficient there. Okay, we got our balanced equation. We need to figure out how many moles we have. Okay, I've got volume molarity of calcium bromide, I've got volume molarity of sodium sulfate, so let's do both. So, we'll make this guy purple. Okay, got my moles of calcium bromide, it's 0.004. Let's do sodium sulfate. Okay, got moles of both reactants. Use the solubility rules. Oh, we already did that, so we already know what the solid is. Determine the theoretical yield of the solid product in grams. All right, so the solid product is calcium sulfate. That is what I should be solving for. So we're going to need mole ratios set up here for both of these reactants. Okay, so the numerator is my solid. My denominator here, I need to cancel calcium bromide. So no change to the number, but the unit changes. Okay, we'll do it again. This time we're canceling sodium sulfate. Again, no change to the number. I get to the point where I have two values for the same solid. You need to assess which one of these is actually possible. Which one is the one I'm going to actually depend on making? You guys remember? Tia?
The smaller one?
Yeah, the smaller one. This is my theoretical yield. That number is fictional. Not done though, because they specifically mentioned they want this in grams. So let's change our moles into grams. A mole, let's see here, 40.08 plus 32.07 plus 64, so 136.11 grams per mole times 0.003. And that is our answer. A lot of times with these longer chemistry problems, the problem in and of itself is just a bunch of little problems slapped together. All right, this is all stuff you've done before. So, let's go ahead and we're going to take some time. I want you to try to work on example 3 and example 4, and we'll give you guys about 20 minutes, and then we'll come back and we'll see what you got.